Alright, Palmer Ridge High School, Mr. Nash's Chemistry, and it is Friday. So we're going to survive. If you're watching this, it's probably Saturday or later. But it's Friday, so I'm going to be alright. A little bit of review to begin with. We talked about the 4 quantum numbers on Thursday in class. First one's the principal quantum number, then your angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So 4 quantum numbers, each one has a different name. Now the principal tells you how big, or the energy level of that orbital that electron likes to hang out in, so kind of how far away from the nucleus. The higher the number, the farther away. The angular momentum gives you the shape of the orbital. The magnetic quantum number gives you the orientation of that orbital, how it's oriented in space three-dimensionally. And the spin quantum number gives you the spin of that electron in that orbital. Positive spin, negative spin, only 2 choices. Remember, orbitals can have different shapes. An s orbital is round or spherical, 3-dimensional. A p orbital was dumbbell shaped or 2-lobed. D orbitals got a little bit more complicated. Most of them were 4-lobed-ish. A couple of them got even more complicated than that. And F's got really complicated. We really haven't even looked at F's yet. Just say they're complicated. Monday we'll come back and I actually have some pictures, some examples for you. So a little bit of review there to get us going. Okay, so looking at electron configurations. On Thursday we looked at orbital filling diagrams, which had the arrows and the circles inside the arrows to represent the electrons in the different orbitals. But I took a lot of writing, a lot of time, a lot of effort. This is shorter, and so hopefully it'll save us some time, and it goes right along with the periodic table. So refer to that. Look at the periodic table often and try to see how they relate to each other. It's really going to help you in the long run. Okay, for electron configuration, just numbers for the energy levels with letters for the orbitals, and to represent the electrons we use superscripts, which are the little numbers at the top. So for hydrogen, we could write hydrogen as a 1s orbital, circle, 1 arrow. There's hydrogen. Instead, we just write 1s squared, because in the 1s orbital it's got 1 electron, so it gets a superscript of 1 to represent that 1 electron. Helium, about the same. We change the scale over to a helium, but it has 2 electrons, so 2 arrows. 2 arrows, so superscript of 2. 1s orbital has 2 electrons in it. Lithium would be Li in the 1s, circle with 2 arrows. In the 2s, I ran out of room over here, circle with 1 arrow. So to represent these 2 electrons in the 1s orbital, we've got that guy. To represent this 1 electron in the 2s orbital, superscript of 1 right there. So giving you the same information, just maybe a little less effort. Let's give oxygen a try. Alright, so for oxygen, oxygen's got a total of 8 electrons. The first 2 are in your 1s orbital, 1 up, 1 down. Next 2 are in your 2s orbital, 1 up, 1 down. Then your 2 p's. Remember, always 3 circles for 3 orbitals. It should have 1, 2, 3, 4 more electrons, so 1, 2, 3, and we double one of them up, 4 electrons. Now to represent that, we would just write 1s squared, 2s squared, 2p. We've got 4 of them up here, so to the 4th power. That represents those 4 electrons. So these 2 are represented by this guy, these 2 represented by that guy, and these 4 represented by that guy. We can double check, add together our superscripts. 2 plus 2 is 4, plus 4 more gives us 8. Should have 8 electrons. Oxygen's atomic number 8, 8 protons, 8 electrons. So you can double check here anytime you wanted. Let's try phosphorus. Okay, so phosphorus, we'll find him on the periodic table. He is atomic number 15. So in the 1s orbital, should have 2 arrows. In the 2s orbital, 2 arrows. 2p orbital, 1, 2, 3, 4, 5, 6 arrows. In our 3s orbital, 2 arrows. And then in our 3p orbitals, 3 circles always for p's. Phosphorus is 1, 2, 3 over, so 1, 2, 3 arrows. Now to represent that, these guys right here, represented by my 1s, 2. These guys right here, represented by 2s, 2. right here, represented by 2p to the 6th power to represent all 6 electrons it contains. This guy right here, represented by my 3s squared. And up here, my 3p's, I've got 3 electrons, so it's to the 3rd power. I can double check. 3 plus 2 is 5, plus 6 is 11, plus 2 more is 13, plus 2 more is 15. It should have 15 electrons, which means 15 protons. Phosphorus is atomic number 15, so everything looks good. Okay, challenge me. Let's take a look at nickel. Now, if I want to do everything for nickel, nickel is atomic number 28, so it should have 28 arrows if I do the orbital filling. So in my 1s, I should have 2 arrows. My 2s, 2 arrows. My 2p's, I should have 1, 2, 3, 4, 5, 6. In my 3s, 2 arrows. In my 3p's, I should have 6 more down there. So 1, 2, 3, 4, 5, 6. I apologize if my arrows are getting sloppy. In my 4s's, 2 arrows. And after my 4s's, what comes next? Remember, the D block's been shifted down 1. So after my 4s's are my 3D's. These are always 5 arrows. And nickel is 1, 2, 3, 4, 5, 6, 7, 8 across in 3D's. So I have to have 8 arrows. 1, 2, 3, 4, 5, 6, 7, 8. So I'd have to draw all that for nickel. Or, to represent these guys, I've got 1s squared, represent those guys, 2s squared, representing them, 2p to the 6th, representing those, 3s squared, to show me these guys right here, 3p to the 6th, show me these guys right here, 4s to the 2nd, and the last one's representing those, 3d, there's 2, 4, 5, 6, 7, 2, 4, 5, 6, 7, is that right? 2, 3, 4, 5, 6, 7, 8. Should have 2, 4, 6, 7, 8. I just can't count. So nickel would look like that. So as you can see, this up here is a lot less work than doing all of that. This is down here is my orbital filling. This is the electron configuration notation. Be careful just because they have different names. Now on the worksheet on Thursday, one of the questions talked about valence electrons. Okay, it's important we know what those are. Those are the outermost principal. Those are the ones in the outermost principal energy level of your atom. Okay, so they're the outermost, farthest ones out. Now, positive nucleus, negative electrons. So the closer electrons, negative, positive, have a stronger attraction. But the outermost ones have the weaker attraction, that positive charge. So in reactions, when electrons are lost, gained, shared, changes happen, it always happens to those outermost electrons. So they're the ones responsible for the chemical properties. Now it's the protons in the nucleus that determine what element it is, but it's the valence electrons that give it the chemical properties. So let's look at some of these. Lithium. Okay, it's electron configuration, 1s2, 2s1. The 2s are the outermost electrons, and so we count up all those, just one valence electron. If we look at oxygen, 1s2, 2s2, 2p to the 4th. So the second again is the outermost, but we count up everything in the second. So the 2s's and the 2p's. So 2 plus 4, 6 valence electrons total. Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. Our outermost is the 3rd principal energy level. So everything in the 3rd, we add up the 3s's and the 3p's for a total of 3 valence electrons. If you want to look at fluorine. Alright, fluorine, right off the periodic table. And it always fills in the same order. So once you get the order down, you've got it. Plus I've got a handout to help you if you struggle with it. But for fluorine, look where it's at on the periodic table. It's going to be 1s squared, 2s squared, 2p to the 5th. So its outermost electrons are in the 2nd principal energy level. So we add 2 plus 5, 7 valence electrons. Then it wanted us to take a look at bromine. So for bromine, bromine's atomic number 35, so it's going to be a little bit longer. So it's going to be 1s squared, 2s squared, 2p to the 6th, 3s squared, 3p to the 6th, 4s2, 3d10, 4p 6. So its outermost electrons are in the 4th principal energy level. So if we add together the s's plus the p's, P5. Oh, I messed up. That should be a 5. 4p5 bromine would be. S's plus p's, 2 plus 5 gives us 7 valence electrons. If you look at a periodic table, look at the back of your book, any periodic table, notice F is right above Br. They're in the same column up and down. Well, we're going to learn in periodic table that a column is called a family or a group. Everybody in the same family or the group should have the same valence electrons. So same family equals same valence electrons. Okay, that's good to remember. It makes things easier. A couple more examples I wanted us to look at. Let's look at krypton and argon. Let's get a blank screen to work with. So krypton, Kr. We find him on the periodic table, atomic number 36. So we write it out, 1s squared, 2s squared, 2p to the 6th, 3s squared, 3p to the 6th, 4s2, 3d10, 4p to the 6th. Okay, that's everything krypton has. So let's look. Highest valence electrons are the 4th. So we add together in the 4th, 2 in the 4s's, plus 6 in the 4p's, 8 valence electrons total. See, the other one I wanted us to do was argon. So let's take a look at argon. Argon is atomic number 18. So we'll go 1s2, 2s2, 2p to the 6th, 3s2, 3p to the 6th. So we look at our highest principal energy level, which would be the 3rd. Add together 2 from the 2s's, 6 or 2 from the 3s's, and 6 from the 3p's. 2 plus 6, 8 again. Because krypton, argon are in the same family, up and down on the periodic table. Anything in the same family should have the same valence electrons. Now krypton and argon are special because they're in that very last family on the periodic table, which is known as the noble gases. The noble gases are kind of special. First off, they're gases. They're all gases at room temperature, but they're very, very unreactive. They don't like to react with anything. The top ones, they can't even get to react. I believe the bottom one, xenon, radon, with enough energy, they've actually got that to react with a few things, but it's very, very hard. They're very unreactive. They'd like to just be left alone. Why? Because their outer level is full of electrons. So they have a filled outer energy levels, which means their outermost S and P energy levels are full. S's hold 2, P's hold 6, so they've got those 8 outer valence electrons, which 8, we call that being an octet. So all the noble gases have an octet of electrons, except for helium up there in the 1s's. 1s only holds 2 valence electrons. That's all he can hold. He's got both of them. He's happy where he's at. All the noble gases very, very unreactive because they have all the electrons they want. They like to just stay where they're at. They don't want to change. They don't want to gain. They don't want to lose. They've got all the electrons they need. Okay, now that we know about noble gases, we can move on to this last idea, which is called the noble gas electron configuration. Okay, it can be even shorter than the electron configuration. Now what you do here, same idea, but you start with a noble gas before the element you're working on, and you put that noble gas in brackets. So if we look at nitrogen, nitrogen's electron configuration will be 1s squared, 2s squared, 2p to the 3rd. Well, we find nitrogen on the periodic table, atomic number 7. The noble gas before that would be helium, atomic number 2. So we put helium in brackets, which represents all the electrons helium would have, which is that 1s squared. And then all we have to do is show what it has after that. So the rest of this right here, we have to represent by writing it after helium. Alright, well that one was kind of silly. It didn't save us much work. So let's give chlorine a try. So if we look at chlorine, atomic number 17. Chlorine would be 1s squared, 2s squared, 2p to the 6th, 3s squared, 3p to the 5th. There's chlorine. Okay, atomic number 17. Let's go to the noble gas before that, which would be neon. Neon is atomic number 10. So by putting neon in brackets, it means it has all the electrons neon has, which represents all of this right here. So all we have to show is what it has after that, so we just have to finish the 3s2, 3p to the 5th. Okay, that wasn't bad. It shortened it up a little bit. I can see where this is maybe helping, but not so much. Let's look at a guy like cesium. We try and do cesium. We find cesium on the periodic table, atomic number 55. So for cesium, alright, stretch, take a break. Alright, cesium would be 1s2, 2s2, 2p to the 6th, 3s2, 3p to the 6th, 4s2, that's an s2, 3d to the 10, 4p to the 6th, 5s2, where's cesium at? Alright, we keep going, 5s2, 4d to the 10, 5p to the 6th, 6s, and cesium is 6s to the 1. So that would be cesium writing it out. In the electron configuration notation, now in the noble gas notation, all we have to do is look at the noble gas before cesium. Cesium is number 55. The noble gas before that would be number 54, xenon. So by putting xenon in brackets, represents all of that. So all we have to write is what it has after xenon, which is the 6s1, all finished, and that guy is a much easier to write than that guy is. So this down here, noble gas notation, this guy up here, electron configuration notation, they're both showing me the same thing, just two different ways to represent it. Alright, one thing you might run into is some books, some worksheets, some professors or teachers might require you to put all your orbitals in number order from lowest to highest. I don't. I always write them in the order that they fill. That makes more sense to me, makes it easier for me to learn them, and hopefully for you guys to learn them. But some books, some teachers, some professors might require you to put them in number order. So let's take a look at zirconium for an example here. Zirconium, Zr, atomic number 40. Alright, so to write the whole thing out, it would be 1s squared, 2s squared, 2p to the 6th, 3s squared, 3p to the 6th, 4s2, that's an s2, 3d10, 4p to the 6th, then we come to 5s2, then 4d, and zirconium is 2 over. Okay, that's the order they fill in, that's the way I write it, that's the way it makes sense to me. Some books will put these in number order though. So I'll start with about the same 1s2, 2s2, 2p to the 6th, 3s2, 3p to the 6th. After 3p to the 6th though, they'll move the 3d's into there. And so we'll have 3d to the 10, and then we'll go back to 4s2, 4p6, and they'll move the 4d's back there. So 4d2, 5s2. So everything's in number order, the 1s and the 2s, then the 3s, and the 4s, then the 5s. And that's fine. To me, these are equal to each other. But to me, this top way makes more sense because it shows the order they fill in from lowest energy to highest energy. That's the way I like to write it. That makes more sense to me. But in some books, some professors might want this bottom method shown. To me, they're equal to each other. But if you see this bottom method in worksheets or the book, don't let it confuse you. It's equal to this top one. But either's fine for me. If you write this bottom one on tests, on worksheets, I'll accept it because to me, they're both correct. So if you see that, please don't let it confuse you. Let's see, last thing. It's important you know the different ways to represent the electrons. On a test, if it says give me the orbital filling and you do the electron configuration, it's wrong. If it says give me the noble gas and you do the orbital filling, it's wrong. So make sure you know the difference between them. The orbital filling is the one that uses the circles and the arrows. And you write it up from lowest energy to highest energy, working its way up the page. So orbital filling, circles, and arrows. The electron configuration is where you write the whole thing out. 1s squared, 2s squared, 2p6, 3s squared, etc. However many that you need, but you have to write the whole thing out. If it wants the noble gas, you have to start with the noble gas before it. So this is noble gas, it has to be the one before it on the periodic table, and then you just show what it has after that. One thing you might run into, I've seen the noble gas configuration where they've asked for that for a noble gas. So it's what's the noble gas configuration for xenon? Well, you can't put xenon in brackets, because saying xenon has all the electrons of xenon doesn't answer a question or explain anything. So you still have to go to the noble gas before xenon. So you'd have to start with the one before that, which would be krypton, and then show the electrons that had after xenon. So if you ever run into that, don't let them trick you, or they're not trying to trick you, but they're trying to get you to think about it. But make sure you know all three different ways to represent the electrons an atom has. Any questions, please come let me know in class. We can talk about it. I'll answer your questions. We'll work it out. But I hope this helps. And Mr. Nash, Chemistry, Palmer Ridge High School, have a great weekend, guys.